Good afternoon, Year 8. It's Mr. Cox back in the science lab today. So, thought I'd do a little video that reinforces what you did for me last week and also introduces something new which is called Ultrasound. So, to start off with it, going over a little bit about waves. So, I've drawn two really bad diagrams here. So, the top one is an example of a longitudinal wave. So, if you imagine you've got a slinky spring and you were to send a pulse down it, you'd have areas where they are squeezed together and areas where the spring is stretched apart. That's a longitudinal wave. Best example of that is a sound wave. That's exactly how sound works. So if I'm talking to you like I am producing vibrations in the air where particles are either squeezed together or pulled apart. And that is a wave. It's a longitudinal wave. Key features you ought to remember from this. So something called a wavelength. That wavelength, definition of wavelength, is the distance of one point on a wave to exactly the same point on the next wave. So on a longitudinal wave, the easiest way of measuring it would be from where they're most compacted to the next time they're most compacted, or you could do it from where they're most far apart. So that is a wavelength. Other features of a longitudinal wave, where they are crushed together is called a compression, which makes sense. Where they are stretched apart is a slightly stranger word called a rarefaction. That's the point where it's most expanded. Okay, so that is a longitudinal wave. Sound is a longitudinal wave. We often process it and display it as a transverse wave because you get more information. So the ghost activity you did for me last week obviously had sound waves but shown as transverse waves. But the actual sound wave itself traveling through the air is a longitudinal wave. Okay, the other type of wave then is transverse wave. Best example of that is a light wave. So light travels as a transverse wave. Effectively what you have is, so I'll jump back to the longitudinal wave again. In this case you have the vibrations moving in the same orientation as the wave appears to go. So if that wave was travelling that way, the particles would be vibrating left and right from my orientation. In a transverse wave, if the wave is moving this way, the particles would vibrate up and down. Obviously, on that, if you imagine you're sitting on the beach and it's a wavy day and there's something floating in the water, it will appear to go up and down, but it does go up and down. The wave will perhaps be moving towards you. So the wave's moving towards you, but the rubber duck perhaps that's floating in it goes up and down. So the particles vibrate at right angles to, perpendicular to the direction of the wave. Other features on there, so again, you've got a wavelength, you can identify on that. So a wavelength is again one point on the wave to the same point on the next wave. So peak to peak or trough to trough is a way, the easiest way of measuring it. You also have something called the rest point. So that's the point where effectively the wave is neither, in simple language, neither up or neither down, neither positive or negative. So that runs in the middle. The distance from there to there, so from the rest point to the top or to the bottom, is called the amplitude. So that is how big the wave is. So bigger amplitude, bigger waves. So if you imagine, think of sea waves again. If you've got a very windy day and you've got big waves coming in, they've got a big amplitude. On a quiet day, they might have lower amplitudes. The thing on there that you can't draw, but the word that you really ought to know is frequency. The frequency of a wave is how many complete waves pass in a second. So effectively, if you imagine that on the beach your waves are coming in, you could count those. The number that pass every second, so if you had a point, say you had your rubber duck floating and you counted every time it reached the top of the wave, that would be your count of the frequency. And so you normally, the unit of it's called is Hz, which is hertz. If something is at 50 hertz, that means that it's one wave is 50 waves are passing every second. Okay. We also use that frequency things like TV refresh rates and stuff like that. So your TV might run at 60 hertz, meaning it refreshes the screen 60 times a second. Okay. So two types of waves. Longitudinal is a sound wave is your best example. The particles vibrate in the same direction that the wave moves, and you have areas of high particle density to low particle density. So I've drawn it as perhaps a spring, but you can imagine it's a sound wave wherever it might be. Transverse wave, waves on the beach. Light waves, all sorts of waves use transverse waves. Particles vibrate perpendicular to the motion, and you can measure the wavelength, the frequency, and the amplitude. And keywords to remember: it's not a top of a wave, it's a peak. It's not a bottom of a wave, it's a trough. Pigs eat out of a trough, same shape. So those are our key features of waves. What I'm now going to do is show you a bit of kit that we would have used had you been in school called a ripper tank, and just show you some wave patterns using that. So we'll do that now. Okay guys, so this is, yeah, sorry, I'll give you a bit off screen here. This is a ripple tone. Basically, it's what you can't really see in the back here. You've got a arm that's attached to a vibrator that will make it basically vibrate at a very particular frequency. So remember, frequency is how many times per second. So we have the ability to adjust that. It's also then got a camera, and there's also a 45-degree angle bit of glass here. So effectively, the reflection will appear on this screen at the front, so we can see the reflection of what vibrations, what waves are travelling through the water. Okay, so that's the how it works. It's called a ripple machine, a ripple tank or ripple machine. I'm going to set this up and we'll just do a couple of experiments to show you a few things about transverse waves. So I've set our ripple tank up, and so remember the little arm here is vibrating in the water, and I've got it set, you can't see the figure at the top, but I've got it set at a frequency of 50, so 50 times a second it's dabbing in and out of the water. You can't probably not see it very clear at the minute. I'm going to do something to sort that for you in a second, but what you see is this is obviously producing waves that travel out from the centre point. What you're seeing is light and dark. Basically they represent the highest or lowest point of the waves. It's a transverse wave, like you'd see if you throw a rock in a puddle of water, travelling out from that point. Okay, so one thing I should have said, this does have quite a funky function. I can synchronise the flashing light that you can see, that's how we can see it. I can synchronise that with the motion of the arm, meaning that the wave will appear not to be moving, which makes it a bit easier to see. So I'm going to synchronise it now. Okay, so hopefully you can see that a bit better. So you can obviously now clearly see we have dark areas and light areas, and those are representing the tops and bottoms of the waves, or as I should probably call them, troughs is the proper word for the bottom, and brain fart, top of the wave is called the peak. So peaks and our troughs. Okay, so that is our standing wave. I can obviously now play with this a little bit and choose this. So if I change the frequency, if I make the frequency slower, or go a bit fuzzy, but you can obviously see the waves effectively, compared to what they were, spread out. If I make the frequency higher, it's dabbing more times a second, and therefore your frequency is higher. So that is effectively we're seeing it looks like it's not moving because of the way we've got it synchronized, but you can now see effectively the wave produced by a single point creating a wave, a transverse wave emanating out from that point. What we're now going to quickly do is change that over, and what if we have two sources producing two different waves so that they interact with each other, and the proper word for that of course is interference. So lunchtime, I'll set that up then with the two dabbers, and we can have a look at the interference patterns you therefore get. Okay guys, what we now have is basically we're creating two sets of transverse waves, so they are now interfering with each other. So you did a bit of work about interference last week's work. So you can obviously see, it's hard to see when they move, so I'll synchronise it in a second, but you hopefully can see that there are areas where the waves are overlapping and therefore reinforcing each other, and areas where they're out of sync and therefore they are cancelling each other out. So if I synchronise it, it's a little bit easier to see. So what you should hopefully see is you've got areas now, sort of streaks coming down, where the waves are, in this case they look darker, means they're higher on the screen, waves that are reinforcing each other and therefore bigger. But you've also got stripes where they are cancelling each other out. So this is a nice real world example of interference where waves are either reinforcing each other and therefore the amplitude is bigger, or they're cancelling each other out, like what happens with noise cancelling headphones, and you are therefore effectively they're out of sync and they destructively interfere and you get no wave. Okay, brilliant. Right, moving on to something new then guys. So next bit of the topic you guys need to know about something called ultrasound. So I'm just going to do a little introduction for you, and then there'll be some work for you to do as well. So, ultrasound. Now, talking about ultrasound, I'm going to start by talking about vision, which seems a bit silly, but you'll see why in a second. So, visible light is transverse wave, okay? So, it's actually part of a whole spectrum, a whole family of waves, and we'll do that in a future lesson, in fact, probably next lesson. Importantly, in the middle, we have what we call visible light. So that's the light that you can see, and obviously you're aware that they are different colours. Those colours have slightly different frequencies. So that means the waves, if it's higher frequency, there are more of them passing in a second, so they're more squeezed together, okay? So, purple light, or violet light I'm going to call it, has a higher frequency and the waves are squeezed closer together. Red light is slightly lower frequency and therefore the waves are slightly further apart and the wavelength is slightly bigger, okay? And there's obviously a graduation between those, so I've kind of just given you three colours, but importantly, at the top is purple or violet and at the bottom is red. Two really handy prefixes to words. Prefix is the bit that goes at the beginning that changes the meaning. So, if you don't know these words, we're about to have them now. We've got ultra and infra. And what those words mean. Ultra means higher than, above. So, we can't see this light, but it exists and you all know it because it gives you a suntan on a sunny day. Above violet light, strangely, is ultra violet light, which has a frequency above that of violet. You can't see it, some animals can. So for instance, there are some flowers that to us might look really dull. In the ultraviolet range, they actually look really bright, and therefore some insects can see into the ultraviolet range. To them, it looks very different to us. You've got red, below frequency is red, infra means below, infrared. Infrared, for us that's heat energy, so that's part of the same family of waves, but infrared waves we associate with things giving out heat, infrared energy. Again, obviously we can, in the military, you can get goggles that will allow you to see infrared, so you can see the heat coming off a person. Okay, so that's the range to do with the what's called the electromagnetic spectrum, because there are waves on above and below each of those. But we're going to do that in a future lesson. But we're going to apply that logic now to hearing. So, humans can hear sounds, but not all sounds. So, if there are remember a sound is a longitudinal wave, not a transverse. Sound be a longitudinal wave. We can hear vibrations. The human range is roughly between 20 hertz and 20,000 hertz. Anything either side of that, our ears won't pick up. And as you get older, actually, that range shrinks, which is why one feature of ultrasound is sometimes they used to do this outside shops. They play a noise that was about 20,000 hertz. Young people could hear it and it'd be really annoying and they'd move away. Old people couldn't, which you might argue is a bit against people's human rights, but there was a quite clever application there of ultrasound. Let's get back to then to what ultrasound is. I think you've already kind of guessed it. There is an all hearing range of that most humans can hear, varying slightly between people, and as you get older it gets worse. Anything above the top of that range is called, in the same way, ultrasound. It is a sound which has a frequency above 20,000 hertz. Humans cannot hear it. So, obviously other animals are different. So dogs can hear well into ultrasound. It's how a dog whistle works. If you blow a dog whistle, you can't hear any noise. It's there, you just can't hear it because your ears can't pick it up. A dog can. That's how a dog whistle works. Below that range, strangely enough, it's called infrasound. Again, we can't hear it because the frequency is too low for our ears to detect and we can't hear it. So, this is just a bit of a brief introduction. Just like light, hearing, there is a range you can hear. Above that, it becomes called ultrasound. There's loads of really useful uses of that. Below that is something called infrasound. Your little job today is going to do a little bit of work, perhaps a bit of research about ultrasound. One last little fact I'll leave you with, which is just interesting. Well, it's a fact, it's more of a theory. For a long time, if there's like, let's say there's a forest fire, often animals would seem to know that that fire was coming a long time before us humans would. So they, all of a sudden, all the birds would fly out the forest and go, oh, why is that? And then an hour later, the fire arrives and it's like, oh yeah, how do they know? Are they psychic? One of the current theories that's actually quite good is that most animals have a hearing range that goes lower than ours into infrasound. If you have something like a forest fire, it actually produces a sound that we can't hear at a very low frequency that travels a very, very long distance. So one of the theories is some of these animals, it's not that they can psychically predict this thing is happening, they hear this very low frequency infrasound that us humans can't hear a long time because it travels further before the thing is obviously visible to us, and therefore they hear it and they leave. Obviously us with not such good hearing, or if I say not such good, not such low frequency hearing, don't detect that sound, and therefore for us the thing gets a lot closer before we perhaps detect it using our own hearing that works within our range. So just a bit of interesting theory for you. So enough of me talking. Rest of your day's work is going to be about ultrasound. It'll be on showing my homework. Have a nice week, guys, and hopefully I'll see you sometime soon. Bye.